Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini, and today's topic is stress and strain moduli. What we're going to be doing is talking about how materials are affected by certain stresses, strains in a given manner. All materials react differently to this. So if I have, let's say, a wire with a weight on the end, obviously there are certain factors that matter as to how far it will stretch. So if I put this weight on it, it was without a weight and it had a certain length, and then I add this weight, of course the factors that matter, there's one intuitive factor you might want to think about, of course, how much weight matters, right? How much force I am putting on it to stretch it matters. The area of the wire, how thick it is, right? And we're going to be using cross-sectional area at least for one type of modulus. But of course, if it's compression, it's going to be volume change for a given area of a surface. That matters, right? The length, how long this is, matters, right? So the thickness and what it is matters, right? So it's important to know how a material reacts under stress and strain. Let's look at with solids. And with solids, we're going to use something called Young's modulus. How something stretches under a given strain. So you see there a force for a particular area. I'll write that over here. Change in length over length initial. That's Young's modulus. So given a certain stress, force for a given area, how much strain is introduced into the material? Let's do an example. Let's say I have a wire. It has a length of 2 meters. Let's say it's steel. And this wire has a radius of 0.5 millimeter. We're going to hang on this wire like I showed in my example on the previous slide. I'm going to hang on this a weight of 10 kilograms. So the question would be, how much does it stretch? Well, in your books you should have a table for the various Young modulus of various materials. We know the Young's modulus of steel based on that table, 20 times 10 to the 10 newtons per meter squared is the Young's modulus. So given all this and given this equation here, I know that 20 times 10 to the 10 is equal to the force, and the force I'm applying on it is 10 kilograms times 9.8 for a given area. Now the cross-sectional area of a wire, if I'm looking straight down into the wire, the cross-sectional area, of course, is pi r squared. Pi times the radius, which is 0.5 times 10 to the negative 3 squared, pi r squared. So that takes care of the force for a particular area. We know the Young's modulus. We put that in there. Change of length for the given length of 2 meters. So as you can see here, I have one variable. So take a couple of minutes. You might want to pause this and see if you can come up with that answer. What is the change of length? Okay. So if you figured that out after pausing this, you should get something like 1.25 millimeters. So that's Young's modulus in a nutshell. And as you see, we have 5 variables here. And I can change, or the problem may have 4 of the 5 variables, and you're solving for the 5th. Okay, so let's move on to another modulus. This is a stress modulus. If I am taking something and I am pushing it off to the side, should call it a shear modulus, right? It's a shear. I'm shearing off to the side. If I put enough pressure on it, it's going to shear a certain amount. If I'm putting a tangential pressure on this, applying a tangential force to shear it off to the side, something that would normally be like a book straight up and down, I've sheared it by a certain amount, a change in distance here. Here's the height. So I am applying a force tangentially for a given area, and the area that I'm using is, if I'm like putting my hand on this and shearing it, it would be that cross-sectional area of the top, for instance. Well, let's do an example of that too. So we're going to still use steel. Let's say this is steel. Still the same force. The force we're going to use is 98 newtons. Applied like we're shearing on the top. Let's say that this is a bar that on the top, if we look at it from the top, is 2 centimeters by 4 centimeters. Has a thickness what we're going to use is the height of 2 centimeters. And I apply this force to it. Shear modulus, force for a given area, causes a change, a shearing for a given height. So we know the force, 98 newtons, 9.8 times 10 kilograms worth of force this way. For a given area, well, the cross-sectional area is 0.04 times 0.02. That's the cross-sectional area that I'm applying this on. So that gives us the force and the cross-sectional area. Change in x is what we're looking for. We don't know that. And we know the height is 0.02. Now, the shear modulus is given to us again. I believe it's 8.2 times 10 to the 10 for steel. So as you can see, if I do this equation, I'm missing only one variable, change of x. So take a minute, see if you could solve this change of x. Put it on pause. You get 2e to the negative 16 meters. Very small. Well, you would expect that. We're not putting that much force. 10 kilograms times gravity if we're doing it. Well, actually, we just said 98 newtons worth of shearing. And if we're doing 98 newtons worth of shearing on a steel bar, that's just not that much force. It's not going to cause much deformation of the material. So 98 newtons of force tangentially, as I'm pressing down and pushing on it sideways, isn't going to cause much problem here on steel. So that's the shear modulus. Again, not much to it. You're going to have 5 variables and know or be able to figure out 4 of the variables. Let's look at something called the bulk modulus. Now, what happens in a bulk modulus is that we're going to have something that is going to compress. Now, this should have a minus sign in here because compression is inward. You're changing its volume. So the bulk modulus is stress under strain, as always, the amount of force we're putting on it. And typically this is something you're measuring in pascals. As you're getting so much force on all the way around a given area, submerging it underwater for a given area. And that's going to change the volume of something from its original volume. How much it's going to deform, how much it's going to decrease in its size. So, as I said, there's a negative here because it is compressing. So let's use that same force, 98 newtons of force on, let's say, we have 1 liter of water. Which is equal to 0.001 meters cubed. There are 1,000 liters in a meter cubed. You should also know a volume of a sphere, by the way. I'm not doing this as an example, but a volume of a sphere. Sometimes you have a sphere 4/3 pi r cubed. You have a sphere submerged, for instance. But for this case, we have 1 liter of water under this much compression, pushing it down, and it's a cube. It's in a cube. And this cube is 0.1 by 0.1 by 0.1 of water. 10 centimeters cubed. So, looking at this equation again, and knowing in the table that we have a bulk modulus for water as equal to 2.2 times 10 to the 9, and that is equal to the force we're giving on this. The force, 98, for a given area, which is the liter cubed, so this comes to 9.8. If you take both of these together, 9.8 times 10 to the 4. Change in volume over what was its volume originally before we put this pressure on it. Well, it's 0.001 meters cubed if you do this math. So the force for a given area, that's this. We have a change of volume for a particular original volume, should lead us to a change in volume. Again, this is negative because we're doing a compression. See if you can figure out this problem. Again, we're putting water under 98 newtons of pressure. Pressure being force for a given area, and that's typically how you get it when you're talking about bulk modulus. We know it to be water, so we have our bulk modulus. We know its volume, how much volume. We have this in a cube, 1 by 1 by 1. Again, it could be a volume in a sphere, or it could be any other material. You're going to need your table for all the modulus. So take a second, figure it out. Again, approximately that the change in volume, of course compression, negative 4.5 e to the negative 8 meters cubed. Volume is in meters cubed. Again, that's pretty small. Water is fairly uncompressible. Even at the bottom of the Mariana Trench, it is not much more compressed in volume than it is at the top, at sea level. So there you have it, the 3 modulus you need to be concerned about. And as I said, you have this table, and you should have this table when you do your assessment, and you're tested on this material. And either you're given the bulk modulus, or maybe you're not given the bulk modulus or the Young's modulus at all, and you're given all the other variables and asked, what is this material? You have to figure out what that material is. Notice we don't have a shear or a Young's modulus for water. Obviously, you can't stretch or strain water in that fashion. Can't deform water in that fashion. You can only compress it. Right? So, as I said, in conclusion, let's keep your modulus handy, that table handy. Understand pressure is in newtons per square meter. Know how to calculate a cross-sectional area, whether it is for volume or for a cube. And practice any examples you have online or in the book. And good luck.